Ceramic materials: structure, classification, properties, and applications. Ceramic materials are among the oldest engineered substances used by humanity and remain indispensable in modern science and technology. Broadly defined, ceramics are inorganic, nonmetallic materials composed primarily of metallic and nonmetallic elements bonded through ionic and covalent interactions. Typical ceramic compounds include oxides, carbides, nitrides, borides, and silicates. Unlike metals, ceramics generally lack free electrons, making them good electrical and thermal insulators, while simultaneously exhibiting high hardness, exceptional thermal stability, and remarkable resistance to chemical attack. The history of ceramics dates back thousands of years. Archaeological discoveries indicate that humans produced fired clay artifacts as early as 24,000 BCE during the Upper Paleolithic period. Early civilizations in Mesopotamia, Egypt, China, and the Indus Valley developed pottery, bricks, tiles, and porcelain for domestic, architectural, and ceremonial purposes. One of the most significant historical developments was the invention of porcelain in China during the Tang and Song dynasties, which later transformed global trade and material culture. In modern times, ceramic science has evolved from traditional pottery and glass production into a highly sophisticated field involving aerospace engineering, electronics, energy systems, biomedical implants, and nanotechnology. Today, ceramic materials are classified into traditional ceramics and advanced or technical ceramics. Traditional ceramics include clay-based products such as pottery, bricks, refractories, cement, and porcelain. Advanced ceramics, by contrast, are engineered materials designed for high-performance applications and include alumina, zirconia, silicon carbide, silicon nitride, piezoelectric ceramics, and ceramic matrix composites. Atomic structure and bonding in ceramics. Their atomic structure and bonding fundamentally govern the properties of ceramics. The two predominant bonding mechanisms in ceramic materials are ionic bonding and covalent bonding. Ionic bonding occurs between atoms with significantly different electronegativities, usually between metals and nonmetals. In this process, electrons are transferred from one atom to another, creating positively charged cations and negatively charged anions that are held together by strong electrostatic forces. Oxide ceramics, such as alumina, Al2O3, and magnesium oxide, MgO, are typical examples of predominantly ionic ceramics. Covalent bonding involves the sharing of electrons between atoms with similar electronegativities. Non-oxide ceramics, such as silicon carbide, SiC, and silicon nitride, Si3N4, exhibit strong covalent bonding. Covalent ceramics generally possess superior hardness, high temperature strength, and chemical inertness. The strength of ionic and covalent bonds contributes to the characteristic properties of ceramics, including high melting temperatures, high elastic modulus, low thermal expansion, and excellent wear resistance. However, these strong directional bonds also restrict plastic deformation, making ceramics brittle and susceptible to catastrophic fracture under tensile or impact loading. Crystalline and non-crystalline ceramics. Ceramics may be categorized according to atomic arrangement into crystalline and non-crystalline materials. Crystalline ceramics. Most engineering ceramics possess crystalline structures in which atoms are arranged in highly ordered repeating patterns. These materials are generally polycrystalline, consisting of numerous grains separated by grain boundaries. Their mechanical and thermal properties strongly depend on grain size, porosity, phase composition, and sintering conditions. Common fabrication methods include powder compaction, followed by sintering, hot pressing, injection molding, tape casting, and slip casting. Crystalline ceramics include alumina, zirconia, silicon carbide, and silicon nitride. Non-crystalline or amorphous ceramics. Non-crystalline ceramics, commonly known as glasses, lack long-range atomic order. Glasses are usually produced by melting raw materials and cooling them rapidly to prevent crystallization. Silicate and borosilicate glasses are the most commercially important examples. Glass processing differs substantially from crystalline ceramic processing because molten glass can be shaped through blowing, casting, pressing, or drawing. Optical fibers, laboratory glassware, smartphone screens, and architectural glass are examples of technologically important glass products. Classification of ceramic materials. Traditional ceramics. Traditional ceramics are primarily clay-based materials manufactured from naturally occurring minerals. These ceramics have been used for millennia and remain essential in construction and domestic applications. Structural ceramics. Structural ceramics include bricks, roof tiles, sewer pipes, and cement products. Their durability, compressive strength, and weather resistance make them suitable for infrastructure and architectural applications. Whitewares. Whitewares comprise porcelain, sanitary ware, tableware, and decorative ceramics. Feldspar, kaolin, quartz, and clay are commonly used raw materials. Porcelain is particularly valued for its translucency, hardness, and chemical resistance. Refractories. Refractory ceramics are designed to withstand extremely high temperatures and corrosive industrial environments. They are widely used in furnaces, kilns, steel-making vessels, glass manufacturing, and petrochemical processing. Common refractory materials include silica, aluminosilicates, magnesia, and zirconia. Advanced or technical ceramics. Advanced ceramics are highly engineered materials designed for specialized industrial applications requiring exceptional mechanical, thermal, electrical, or biological performance. Oxide ceramics. Oxide ceramics are composed primarily of metal oxides. Important examples include alumina, Al2O3, zirconia, ZrO2, beryllia, BeO, and titania, TiO2. Alumina is one of the most widely used engineering ceramics because of its hardness, corrosion resistance, and electrical insulation properties. Zirconia is notable for its transformation toughening mechanism, which significantly improves fracture resistance compared with conventional ceramics. Non-oxide ceramics. Non-oxide ceramics include carbides, nitrides, borides, and silicides. These materials exhibit superior hardness, high-temperature stability, and wear resistance. Silicon carbide is widely used in abrasives, high-temperature components, and semiconductor applications. Boron carbide is among the hardest known materials and is used in ballistic armor. Silicon nitride is valued for its thermal shock resistance and is commonly employed in turbine components and engine bearings. Ceramic matrix composites. Ceramic matrix composites, CMCs, are produced by reinforcing ceramic matrices with ceramic fibers or particles to improve toughness and thermal shock resistance. These composites are increasingly used in aerospace turbines, hypersonic vehicles, and thermal protection systems because they maintain strength at temperatures beyond the limits of metallic alloys. Properties of ceramic materials. Ceramics possess a unique combination of physical, chemical, and mechanical properties. Mechanical properties. Ceramics are extremely hard and exhibit excellent resistance to abrasion, erosion, and wear. Their high compressive strength makes them ideal for structural applications subjected to compressive loads. However, Ceramics generally possess low tensile strength and poor impact resistance because cracks propagate rapidly through their brittle structures. The elastic modulus of ceramics is typically higher than that of polymers and many metals, contributing to their rigidity and dimensional stability. Thermal properties. Ceramics generally exhibit high melting temperatures and excellent thermal stability. Many ceramics remain structurally stable at temperatures exceeding 1,500 degrees Celsius. Their low thermal expansion coefficients make them suitable for applications requiring dimensional precision under thermal cycling. Certain advanced ceramics, such as zirconia-based thermal barrier coatings, protect turbine blades and aerospace components from extreme heat exposure. Electrical properties. Most ceramics are excellent electrical insulators because they lack free charge carriers. This property enables their extensive use in electrical insulators, capacitors, spark plugs, and circuit substrates. Some ceramics possess specialized electrical behavior. Barium titanate, BaTiO3, exhibits ferroelectric and piezoelectric properties, enabling its use in capacitors, sensors, and actuators. Yttrium barium copper oxide, YBA2Cu307, is a high-temperature superconducting ceramic capable of conducting electricity with zero resistance below its critical temperature. Chemical resistance. Ceramics are highly resistant to corrosion, oxidation, and chemical attack. Unlike metals, they do not readily rust or degrade in aggressive environments. This chemical inertness makes ceramics valuable in chemical reactors, biomedical implants, and high-temperature processing equipment. Optical properties. Many ceramics exhibit important optical properties. Sapphire and transparent alumina are used in infrared windows and optical systems. Glass ceramics and optical fibers have revolutionized telecommunications by enabling rapid transmission of information through light signals. Processing and manufacturing of ceramics. Ceramic manufacturing typically involves powder preparation, forming, drying, and high-temperature firing or sintering. During sintering, particles bond together through diffusion processes, producing dense, solid structures. Common ceramic processing techniques include dry pressing, slip casting, tape casting, extrusion, injection molding, hot pressing, and additive manufacturing. Recent advances in nanotechnology and colloidal processing have improved the mechanical reliability and microstructural control of advanced ceramics. The microstructure produced during processing strongly influences density, grain size, fracture toughness, optical transparency, and electrical behavior. Applications of ceramic materials. Construction and architecture. Traditional ceramics, such as bricks, cement, tiles, and sanitary ware, are foundational materials in modern construction. Their durability, weather resistance, and fire resistance make them indispensable in infrastructure and housing. Aerospace and defense. Advanced ceramics are critical in aerospace engineering because of their low density and resistance to extreme temperatures. Ceramic matrix composites are used in jet engines, turbine blades, rocket nozzles, and thermal protection systems for spacecraft. Ceramic armor composed of boron carbide, alumina, and silicon carbide provides ballistic protection in military vehicles and personal body armor. Electronics and telecommunications. Electronic ceramics are essential in capacitors, semiconductors, piezoelectric sensors, magnetic devices, and integrated circuit substrates. Ceramic insulators are widely used in power transmission systems. Optical fiber technology, based largely on silica glass, transformed global communications by enabling high-speed data transmission across continents. Biomedical applications. Bioceramics such as alumina, zirconia, hydroxyapatite, and bioactive glass are extensively used in orthopedic implants, dental restorations, and bone graft substitutes. Their chemical stability and biocompatibility allow long-term implantation within the human body. Zirconia crowns and all-ceramic dental prostheses have become increasingly popular because they combine excellent aesthetics with high mechanical strength. Energy and environmental applications. Ceramics play vital roles in energy generation and environmental protection. Solid oxide fuel cells employ ceramic electrolytes for efficient energy conversion. Catalytic converter substrates made from cordierite ceramics reduce harmful automobile emissions. Nuclear reactors utilize uranium dioxide, UO2, ceramic fuel pellets because of their high-temperature stability and radiation resistance. Industrial and tribological applications. Ceramics are extensively used in bearings, cutting tools, wear-resistant coatings, seals, and abrasive systems. Their high hardness and resistance to friction-induced degradation make them ideal for tribological applications. Silicon nitride bearings, for example, offer superior performance in high-speed and high-temperature environments compared with conventional steel bearings. Limitations of ceramic materials. Despite their many advantages, ceramics possess several limitations. Brittleness remains the most significant drawback, limiting their ability to withstand impact or tensile stress. Their low fracture toughness often necessitates reinforcement through composites or transformation toughening mechanisms. Machining ceramics is also difficult because of their hardness, often requiring diamond-based cutting tools or specialized processing methods. Furthermore, some advanced ceramics remain expensive due to energy-intensive manufacturing processes and strict purity requirements. Recent developments and future perspectives. Modern ceramic research focuses on improving toughness, reliability, multifunctionality, and manufacturability. Nanostructured ceramics, additive manufacturing, self-healing ceramics, and ultra-high-temperature ceramics are rapidly expanding research areas. Additive manufacturing technologies now enable the fabrication of complex ceramic components for aerospace, biomedical, and electronic applications. Researchers are also developing environmentally sustainable ceramic processing routes that reduce energy consumption and greenhouse gas emissions. The integration of ceramics with nanotechnology, biomaterials, and quantum electronics is expected to further expand their applications in medicine, renewable energy, and advanced computing. In conclusion, ceramic materials have evolved from ancient clay artifacts into highly engineered materials essential to modern civilization. Their unique combination of hardness, thermal stability, chemical inertness, electrical insulation, and wear resistance makes them indispensable across industries ranging from construction and transportation to electronics, medicine, aerospace, and energy systems. Traditional ceramics continue to support infrastructure and domestic life, while advanced ceramics drive technological innovation in demanding engineering applications. Although brittleness and processing challenges remain important limitations, ongoing advances in ceramic science and engineering continue to improve their performance and expand their industrial significance.